Okay, well, it's recording. Anyway, so let me read the beginning part, and then I'll have you guys read some chapter or some paragraphs out loud to the whole class. So chapter 2 will help you develop the power to manipulate functions. When it says manipulate, what's really meant by is transformations. And you guys have actually done some of this stuff in geometry and algebra 1. Especially if you've done CPM for a middle school or CPM last year in geometry. So it shouldn't be too new to what they're going to talk about. So we're going to manipulate functions so that they're useful in a wide variety of situations. In the first section, which is obviously today, you'll learn how to change the equation of a parabola to make it fit a set of nonlinear data. So we're going to take a parabola and move things around. We're going to move it left to right, up and down. We're going to stretch it. We're going to flip it. So like stretch, compress, reflect, shift, all those things. And we're only focusing on y equals x squared today. Okay, we're going to keep it really simple. Y equals x squared, you guys should know how that looks. Just a parabola, right? The vertex is at 0, 0. If you made a quick table for it, you don't have to copy the table if you don't want to. But if I plug in 0, I get 0. Plug in 1, I get 1. Plug in -1, I also get 1. Plug in 2, I get 4. Plug in -2, I get 4 as well. So there's a good deal of symmetry that's going on with these graphs. And we're going to be transforming those graphs today. You'll learn that graph transformations are clearly recognizable when this equation is written in graphing form or the vertex form. The vertex form, this I do want you guys copying somewhere in your notes. This is actually very important because we're going to see this format used for other equations as well. So you have A, H, and K. I'll explain what A, H, and K do in just a little bit, not right now. But that's going to be the graphing form or the vertex form of a parabola. And we're going to be using that to shift graphs or stretch them or flip them over, all that stuff. Understand this form will help you to rewrite equations so that they're easier to graph. You'll also be able to use the quadratic family of functions to model physical situations. So we're going to talk about projectile motion. A lot of you guys play sports. So like how a football travels, if you're kicking a football or throwing it, or baseball, how that travels, soccer ball or volleyball, water polo, like all these different sports uses projectile motion. So we're going to be looking at that and how quadratic functions use to model the movement of those objects. And then not next week, but really Wednesday and Thursday, we'll be looking at other functions that we'll be moving around. Okay, so I'm going to give my voice a little bit of a break and have some of you guys read the next parts. And we're going to do this page together. The second page is more fluff, to be honest with you. I'm going to kind of give you guys some more details and information of how to do transformations. The third page is what you're going to do in groups. And then, of course, homework follows after that. So this should go by pretty smoothly. All right. Anyway, before we do the Parabola Lab Part 1, let me have you guys have someone read for me because I need to give my voice a break. I tried. Do you want to read where it says what happens?
Yeah.
Yeah. Thanks.
What happens to a parabola graph when you change the numbers in the equation? You get a better sense of different ways to transform the graph of the parabola. As a team, complete the investigation outline below. As you work, be sure to sketch the graphs you see in your graphing calculator carefully and record the equations you have.
Okay, one thing we need for sure, we need at least one graphing calculator per table. So if someone has a graphing calculator, please take it out. I mean, the more the better, but at least one per table. I'm going to use Desmos because it's easier for me to show you what's happening. But I think you guys are pretty comfortable graphing the calculator. I'll pull up the graph calculator too anyway. So we're going to graph the following. We're not going to do this on graph paper. We're just going to do it on the graphing calculator instead. So forget about on a large graph paper. So we'll say y equals x minus 2 times x minus 2, which, by the way, is x minus 2 squared. So we're going to graph that in the calculator. The way you would do it, it's really simple. Turn on the calculator, go to y equals, and you punch in x minus 2 times x minus 2, or you do parentheses x minus 2 raised to the second power. Same thing, right? No different. And hit graph. Where do you see it touching the x-axis, by the way? What's the x-intercept of this graph? 2. Yep. It's at 2, 0. Well, based upon the graph we see, right? So I know you're saying -2 because you see a -2. It's actually going to be +2 because if you plug 2 into the equation, what's 2 minus 2? 0. 0. That's right. It's 2 compared to 0, right? Yeah, that was a Josh McDaniel, dude. Sorry. Oh, I know, right? Okay, so the graph looks like this. It crosses the y-axis at 4. Here we go. So that's how the graph will look. I'm going to do it on Desmos because it's easy for you guys to see what's happening. But that's how you try graph in the calculator. So let me go to Desmos really quickly. I should have it up already. Nope, I don't. So y equals parentheses x minus 2 squared. Okay. So there you go, right? There's the graph. It crosses the x-axis at 2, the y-axis at 4. And by the way, there's another point at 4, 4, 4, right? Because we need to have symmetry, right? Very important. Whatever you have on one side of the graph, you have to have on the other side to maintain the symmetry. Because you're squaring something, you're going to have a lot of symmetry here. Anyway, let's actually do the real hard of the matter, B through G. So part B is asking you, use your graphing calculator to find the equation of two problems with different graphs that also open up or solve vertex 2, 0. And by the way, going back to part A again, I forgot to mention this. So the graph looks like this one more time, right? Here's a graph, 1, 2, 3, 4, 1, 2, 3, 4. So let's go back to A. Sorry, I was supposed to do this with you guys. I'll just generate the graph again for part A. Okay, this line right here that I'm drawing, what's the equation of this line right here? This dashed vertical line. What would be the equation of that dashed vertical line, guys? That's hard to see. Yeah, let me do a better color. That's really hard to see. It's x equals 2 because it's crossing the x-axis at 2. That's a little better. So the line of symmetry is x equals 2. And that's going to be very important because we need to actually see how the graph moves with that. Okay, now let's do part B. Part A is done. The vertex was 2, 0, right? We know this. The sketch we got, the line of symmetry we got. So now let's look at part B. Use your graphing calculator to find equations of two more parabolas where the graphs are different, but still opens up and still has a vertex 2, 0. So let's go back to Desmos. Let me go ahead and clear my screen. And I'm asking you guys, what can I do to this equation so that it still touches at 2, 0? It still opens up, but it's a different graph. It's not the same graph. How can I change this equation so that it still has everything else that's roughly the same, the vertex and opening up, but still not quite the same graph? Go, Chris? Yeah. What do you mean by the range, actually? So what do you want to do to the equation, I guess? That's. Do you want to add something or multiply something? Well, let's try it. Just give me that. Let's do it. I like that. Let's have. If I added a number, so what happens to the graph now? It went up, right? So that changes the vertex. I don't want to do that. And actually, let me use a second equation. So let me copy and paste the first one here. Okay. Yeah, if you added, that does change the vertex. But we're going to talk about that because that's important too. Or if I do -1, that also changes things. But what if I put something to the left here? What if I put 2? Did the vertex stay the same? Yes. Did it open up? Yes. Is it the same graph? No, which is what we're trying to do. Or what if I did like 0.5? Or what if I put a negative? Actually, I don't want that because we want opening up. So what you could do is you could change the number in front to definitely get a different type of graph that still has the same vertex and still opens up. So coming back to the notes again, for part B, we already did part A. Write two more equations with different graphs, but also opens up and has a vertex 2, 0. You could say y equals 2x minus 2 squared. Or you could say y equals, say, 0.5. So what did that do to the graph visually? Like what did you notice? How did it change compared to y equals x squared when you put these numbers in front? What kind of change is that? It does get steeper. More specific, it's probably going to change the width of the graph, right? So for part B, we changed the width of the graph. And by the way, down below, I'm going to write the general equation again, which I shared with you guys just a few minutes ago. So what did we change? We changed the letter A. A impacts the width of the graph. The number in front changes the width of the graph. Now let's look at part C. Part C is add the sketches, blah, blah, blah. Don't worry about it. Let's just move on. Part D, now what do we want to do in part D? We want to have the graph open downwards. Still the same vertex, touching the x-axis at 2. how would I make the equation different so that it opens down? What would I do in this case? What do you guys? A negative, yes. If you simply put a negative out in front, guess what happens? The graph looks like this now. So what does that do? It also causes a reflection. And I'll be more explicit. A reflection about the x-axis. And that happens when a is negative. When a is negative, that causes it to flip up the x-axis. But more formally, you say reflect. Don't say flip, it's not as sophisticated. We want to say reflect. It reflects about the x-axis. And you have to specify about what axis, because you can flip about the y-axis. Now that's a different thing, which we won't talk about today. Is there a question? Yeah, go ahead, Lillian. Yeah. Sure, yeah. Totally, 100%. And we're going to get there. Totally, 100%. Yeah, and let me just go back to Desmos. I'll clear my screen for a moment. So go back to Desmos and change that to a negative. There you go. It opens down, right? Still kept the same vertex, but now it points down because all the y values which were positive to begin with now become negative for the PEMDAS, right? You square, great. Maybe you square stays positive, but then multiply by -1, the y values go from positive to negative. And we'll talk about how the table will change at another day. We won't do that today. Today, we just wanted to see how the graphs change. Okay, let's go back to the notes. Let me undo my erasings. Okay, so part E, so D is done. Part E, add and blah, blah, blah. That's fine. And the line of symmetry is still x equals 2, right? We didn't move the graph horizontally yet. All we did was we stretched the graph, right? We stretched it or widened it before we flipped, right? That's all we've done so far. Let's look at part F. Now, part F, we want to do a few things. We want to have it go down and move the vertex. So we want to do two things, actually. So let me go and clear the screen here. Let me reposition the page. So now what we want to do is we want to do two things. We want to go down and move the vertex. So we have to shift 4 left or shift to -4 for x and open down. So looking at the graph here, going back to Desmos one more time. Let me clear. How am I going to type the equation? So right now, it's at 2, 0, right? Because when you plug in 2 for x, you get 0. That's obvious. 2 minus 2 is 0, 0 squared is 0. So that kind of helps us find the vertex when you see that 2 there. What would I type if I wanted to have the graph go down and also touch -4 on the x-axis? So yes, I need a negative for sure. Good, excellent, you got it, yes. -x plus 4 squared. Excellent. Oh, whoa, that's crazy. There we go, yeah.
Well, it's almost like they only do it.
That's pretty close, yeah. That wasn't great, but it's okay. It's good enough. Yeah, -x plus 4 squared, right? Because what's happening is that the plus 4, if I play a -4 now, what's -4 plus 4? 0. What's 0 squared? 0. And negative cares, it's still 0. So the plus is kind of counterintuitive. I see a plus 4, it actually means left 4. The -2, that's also counterintuitive. I see a -2, but it's actually right, so it's total opposite, totally. Yeah, it's a bit counterintuitive when you change x. That means a -4 to the left. Sorry, 4 to the left. That means 2 to the right. And the a value changes it, whether it goes up or down. So going back to this again, y equals ax minus h squared plus k. We now see that h affects the graph horizontally. That's a horizontal shift. We see that a affects the graph by vertically stretching or reflection. What do you think k does, guys? And so Lillian, this gets to your question now. What do you think k does? Vertical shift, totally, right. Because you're adding or subtracting a number to the whole thing, right? So if I put a +1 on the right side of this, there you go, moves up 1. Or if I put a +4, moves up 4. So that's totally intuitive. But the inside's counterintuitive. -2 means 2 right, +4 means 4 left. And I'm going to repeat all the stuff. Don't worry. I'm going to actually summarize this on the next page. Vertical, sorry. But I'm going to write this again on the next page. So don't worry about it. I'm going to repeat this and I'll write more nicely on the next page. Okay, so going back to this one more time. Now, for part G, and line symmetry by was x equals -4 for part F. Sorry about that. Choose a new point on the x-axis. Find at least 3 equations. Don't worry about it. Let's just skip it because we're going to do this again on the next page. Okay, this is super corny, so please bear with the corniness here. And Elliot, I'll have you read since you just got back in the room. Okay, so if you could read the first paragraph, polyparabola. Yeah, and give the chair back. Yeah. Well, great. Right, so polyparabola. I know it's very corny, but just let's read it. Just the first part, the top part.
Polyparabola. The manager of the parabola department of functions of America. She has decided to start her own company called Professional Parabola Production. She needs your help. See your memo below.
Okay. I also want to read the memo now. But thank you. No, you're good. You're good. Lucas, you want to read part of the memo?
Sure.
You say I can read with the I'm starting.
I'm starting a company specializing only in parabolas. When I have new customers, I need to be able to show them that we know more about parabolas than any of the other function factors around, especially since every company already sells y equals x squared.
Okay, and then Nava, can you read the next part? Yeah, and I'll finish it off. Please investigate all different kinds of parabolas, determine all the ways that you can change the equation. That's a big one. That's what we're working on today. All the ways you could change the equations, y equals x squared. So you could look at the shape, direction, location of the new parabola. Remember, I'm counting on you. I need to uncover the parabola secrets that our competitors do not know. Sincerely, Ms. Polyparabola. Okay, very corny. That's okay. This is the part that I think matters a lot to me. How do we change the graphs? What's a summary of all the changes and how that correlates to the general equation I shared with you guys a few moments ago, the y equals a parentheses x minus h squared plus k. So it says work with your partner or your table groups. That's what you're going to do. To determine all the ways you could change the parabola by changing the equation. So generally speaking, the equation looks like this again: y equals a x minus h squared plus k. I'm going to explain what h, k, and a do in just a little bit. But let's talk about all the different ways you can change it. I'm going to get a style set so I look very better. My hand going inside the mouse. Okay, so let's talk about all the ways we're going to change graph. We are going to talk about horizontal shifts. So we're going to move the graph either left or right. We're also going to talk about vertical shifts. So either going up or down. Oh, it's so much better with the stylus. Here we go. We're also going to talk about vertical stretch or compress. We're also going to talk about reflection. About the x-axis. This is true for any kind of function, not just y equals x squared. For 5, any combination of numbers 1 through 4. So you got to be comfortable with that too. Now, for the first one, that's going to be solely about h. If h is positive, you go right. If h is negative, you go left. That should be intuitive, hopefully, right? This here is going to be k. If k is positive, where do I go? Up. And if it's negative, down. This is going to be for a. If a is bigger than 1, we stretch. If it's between 0 and 1, you compress. And lastly, for this one, A is negative. So those are the summary of changes, okay? These are the changes we'll be working through for all types of functions throughout the next 2-3 weeks. So again, horizontal shift is purely determined by H, vertical shift is determined by K, vertical stretch is determined by A or compressed, and phase negative.
Does that say
Good.
under compressed on the bottom?
Negative. Negative? A is negative?
Oh,
Oh, 0 is less than A. Ooh, yeah, that's hard to read. A is between 0 and 1. Sorry about that. Let me change the color so it stands out a little more. So 0 is less than A. Is that better? Yeah, there we go. Yeah, that's what's happening. So when A is a fraction between 0 and 1, that's going to be a compression. So those are the changes we have to look at. And this is the big one. This is the general equation right here. That's the general equation. A times x minus a squared plus k. Before we do page 2, which I'm going to have you guys do in table groups, let me just go through Desmos one more time. Let's look at y equals x squared, which is just this, right? There we go. So for example, what if I do this? That goes down, right? That gets skinnier. That gets wider, compressed. If I do this, up, up, down, down, right? Or if I do inside, like this here, that's right 1, right 2, right 3, right 4. Left 1, left 2, left 3, left 4, and so forth. If I do a whole bunch of things, like a negative 2, x plus 1, minus 2, what I do here? I went 1 left. I went 2 down. I flipped it over. I also made it skinnier. I did a lot of different things here, right? The plus 1 is counterintuitive. You see a plus 1, don't go right 1. You go left 1. Why do I go left 1? Because I got to plug a negative 1 in for x negative. That's why I go to left 1. The plus 2 is intuitive, though. Go up and down, depending on what you see. All right. So what you're going to do in the 3rd page of these notes, and then we'll start homework after this. What are you guys going to do? You're always going to work with y equals x squared, just so you know. Every single time working with y equals x squared. Don't know why I didn't print. That's so weird. Or maybe they meant to put the boxes. I don't know. So your job is to make a new equation for each scenario described below. Okay. Use a graph calculator if you need to. Do this in your table groups. I'll come around in a few minutes to see how things are going. I'll put the answers up, and then we'll be done with the notes for today. Yeah, so you could do this, guys. You could say y equals 2x squared. It's getting narrower as a result. Y equals 0.5x squared if you compress. That's getting wider as a result. If you want to open down, you could do y equals negative x squared. The vertex is now a maximum, by the way, because it's pointing down. That's pretty obvious. If you want to go 5 units down, that's y equals x squared minus 5. Hopefully you guys got that. The new vertex is going to be 0, negative 5. But if you go 5 units up, it's going to be y equals x squared plus 5 now, right?
So 5 units down, would you do y equals
X squared.
Oh, I was looking at the wrong. I was looking at the C.
Yeah, that's good. Oh, good. Oh, yeah, go ahead. Okay, let me move the screen down a tad, and I'll just readjust. So you guys are still copying. That's fine. Delete. Here we go. Okay. For part E. Oh, don't. Yeah, thank you. Appreciate it. Okay. If you're going 3 units to the right, Now, careful here. That'd be y equals x what? Actually, -3. That's to the right.
It's like, so yes, it's opposite.
It's always opposite. So that's 3, 0. Yeah, when you're going to the right, I know it sounds counterintuitive, I get it. But things that, in order to make that 0 for y, get the same vertex as a function, you have to plug in 3 for x. 3 minus 3 is 0, right? That's why it's a -3. I know it seems counterintuitive, but if you put a plus, it's going to go left. So if you want to go left, I'll change color so it stands out a little bit. If you want to go 3 and it's left, what would that equation be, guys? Y equals +3, exactly. And Cooper, I made a recording, so I'll just share the recording. Don't worry about it, because we're almost done with the notes. Now, if you want to go 3 units to the left and stretch vertically, you do y equals, go back to blue. Y equals, you could put a 2 in front if you want, and x +3 squared.
Wait, 3 squared? Oh.
Because it said go 3 units left. So you do that for f. That's a possibility. G is a doozy. You want? Yeah, go ahead. Yeah, go right, yeah, please. Sure. Oh, for part G. Let's see. Y equals. Actually, you're close. You want to do -1/2. Close price. I'll explain why in a sec. Okay, before I do part G, any questions about E and F? We're okay at the E and F? Okay, let's look at G really quickly and we'll start the homework. And timing is good. Because I think we end class 2:05. Okay. So G. So again, you're looking at y equals x squared as a parent function, the most basic parabola, right, that we can make. And remember, the general rule is this. And if I need to summarize, I'll summarize one more time for you guys. A changes the graph. That's a vertical stretch or compress. / compress. Or a reflection about the x-axis. I want to be very explicit here so you guys are not confused. Because you can reflect about y-axis, it's a different thing. We won't talk about that today. H is a horizontal shift. There's a minus next to it, so you have to be counterintuitive there. And K is a vertical shift. So just summarizing that one more time from page 2. And here's the general formula. Now, you're going downward.
So negative.
So A is negative. But negative what? -2 or -0.5? It's -0.5. Here's the reason why. You're compressing that stretch. Because you're compressing, it's the half as much.
Oh, so that's why vertically compressed is on top.
Yes, yes. You're smushing it down the half. Yeah. So guys, compressing is less than 1. Okay, what's K here, guys? If we're going 6 units up, what's K going to be? +6. And if we're going 2 units left, H is going to be what? Well, it's going to be -2, but +2 in the equation. H itself is -2, though. So the equation will be y equals -0.5 x + 2, because you're doing x minus -2, which is x + 2, +6. So H is still somewhat intuitive. You're going left, so yeah, make it -2, right? That's on page 2. Things are good. You can do -0.5, it's fine. Okay, yeah, I don't care. That doesn't matter to me. But yeah, when you're going left to, you got to put H -2, but then when you put it into a formula, it's -2, which is a +2. I know it's a little weird. That's what's happening. If I go back to Desmos really quickly, just make sense of all this. So let's go make a new equation. -1/2 x + 2. Come on. X + 2 raised to the second power +6. Let me clear my screen because it's a little busy here. And there you go. That totally went 2 left.
The totally went 6 up. It definitely got wider, and it's pointed down.
We'll start talking about tables, how the table gets adjusted, because we do have a table we can do for y equals x squared. The table will get adjusted for the new graph. We'll talk about that at a later time. I'm not going to do that today. Right now, we're just visualizing what's happening. I don't want to overwhelm with too much information. But yeah, and then let me undo my writing. So there we go. That's the answer, -½ x plus 2 squared plus 6. Okay, we got about 20 minutes left, so plenty of time to get head start homework, especially if you want to watch football tonight or got other stuff going on tomorrow. It's not great. It's let me stop the recording.